Hello and welcome to Technically Speaking, a podcast where scientists and engineers come together to chat about a common interest, share knowledge and satisfy some curiosity. I'm Aneeqa, and in this episode, I'm joined by Jennifer and Laura to talk about solar cells and their sustainability. So to start off with, Jennifer, why do you care about solar cells and what's your interest in them?
I personally have a background in research. I used to characterize perovskites that were mainly used for solar energy applications.
Awesome. And Laura, what about yourself?
Well, I've never worked with them. I've heard a lot about them at material science conferences that I've attended. And I really like the idea of my house being like completely self-sufficient and generating its own electricity. But I've not really been entirely convinced that I could do that with just solar panels alone. And my bills are quite low anyway. So buying more technology for me doesn't really seem like a good idea if I want to become this amazingly carbon neutral, completely self-sufficient, sustainable household.
That's the dream, right? I think for a lot of us, and especially with the electricity prices are going through the roof at the moment. So maybe there will be a kind of tipping point in the future where it would be kind of more cost effective in order to be able to do that. Before I go completely off on another tangent, maybe we can start with defining what is a solar cell. Laura, do you know what it is?
Those solar panels that people have on their roofs, they're made of quite a few things, but what I heard about at conferences was the important bit is this the semiconductor material that's usually made from silicon.
Okay.
So that's the bit that conducts electricity when sunlight shines on it. And apparently it's called a semiconductor because it conducts as much as an insulator, but not as much as a conductor, which I find a bit of a circular definition, but there you go.
Okay. So I never knew that actually. So traditionally, solar cells are made of silicon. Why? Is it because they're a semiconductor? Is there any other reasons?
I was trying to read into this before, and it's definitely not my background, and it's not something that came up in the materials science conferences that I remember. But there's a limit that I think was calculated by two people whose names I'm not going to pronounce because I'm not sure how to pronounce them. They defined this limit using what's the wavelengths of energy coming from the sun? What's the different wavelengths of visible light? Mm-hmm. How can you absorb as much of that light as possible? And what other effects do you have to account for? And there's something called a band gap in these semiconductors, which is the difference in energy between the electrons that are really closely bound to the nucleus of the atom, and then the ones that are further away, the electrons that can move around, the so-called valence bands. That band gap is to be most efficient at turning photons of light into electricity. That band gap is about 1.1 electron volts, which is what pure crystalline silicon gives you. That's why silicon. I think it's also one of the most abundant elements on Earth, so that's handy. We're not having to do a lot of refining. We're not having to look really hard for silicon. We can find it pretty much anywhere, and then it just needs to be purified to get it really, really pure.
Awesome. It seems a bit of a wonder material that you can use it for solar cells. We also have Silicon Valley, where I guess they make the chips and computers from them. I only know because, again, this week I was watching another K-drama and they go to Silicon Valley in that one. It's called Startup. Great drama if anyone wants to watch it. Okay, so silicon is kind of the conventional material. Jennifer, you mentioned something called perovskite at the beginning, which you used to do work on. Is that another type of material that we can use to make solar cells?
Yes, it's another type of semiconductor material. A lot of people haven't heard of perovskites. Most people know about silicon-based solar cells. It's not surprising since the potential of using perovskites as light absorbers for solar energy applications was first discovered in 2009.
Oh.
So that's not even 2 decades ago. The researcher who led this discovery was Aneeqa. And the efficiency of perovskite solar cell devices at this time was 3.8%. And 6 years after this first discovery of the perovskite solar cell devices, the conversion efficiency reached 22.1%. This kind of increase hasn't been seen with any other type of solar cells, including silicon. But I mean, that might be due to technological advancements in research. I mean, the first silicon-based solar cells were produced in the 1950s, and technology has come a long way since then.
That's crazy. And is 22% good? Or do we need to have higher if we can use those instead of silicon.
That was 6 years after the first discovery, but nowadays it's on par with silicon, at least for single crystalline silicon, or single crystal silicon. So perovskite solar cells has an efficiency today of around 25.7%, whereas single crystal silicon solar cells have an efficiency of 26.1%. So there's a difference of about 0.5% in efficiency. So they're almost at the same level.
I think I'd read that the absolute limit of efficiency for silicon-based solar cells is about 30%, I think. So do you know if it's the same for perovskites, Jennifer? Or is the theoretical maximum higher?
I'm not actually sure, but I know that that kind of maximum can be surpassed if we use tandem or multi-junction solar cells where we combine several photon absorbers. And then for that, I know that the efficiency is around probably around 40%, maybe above that even. So it's
wow.
Quite high, yeah. But this is in a lab, like really strict research lab conditions. So it might differ in more, let's say, production environments.
Yeah, of course. So silicon is used pretty extensively. Perovskites are catching up to silicon now. They can get the same levels of efficiency. So will we start seeing perovskites in the solar cells that we see around us?
Well, there's still a bit of a way to go, because there are still some struggles with the stability. I mentioned the first set of perovskite solar cells that were produced in 2009. These first set of perovskite solar cells only lasted a couple of minutes before they started to degrade. But now they can last for 1,000 hours, a few cycles. There are still some things that need to be improved in terms of stability before they can become more popular commercially.
Yeah, I guess that would be a huge issue for you, Laura, if you put your solar panels on your house and every week you're having to change them. I wouldn't want to be climbing up onto the roof every single week to change solar cells. There's so many things that we have to take into consideration when making this technology going forward. I also just want to add, as a side, from my very limited experience of solar cells, I did some research a while ago on tungsten fuzz, which is this kind of nanostructure that forms inside fusion reactors. It turns the tungsten black, and so it has this potential for photovoltaic applications, which I thought was very exciting. So it's like something that might be bad in one field can be good in another, which I think is really important to remember as scientists, because sometimes we get really disappointed with our results, or we see something that's not ideal for our application, but we should also try and think if there's other applications that may find it useful. That was a bit of a tangent. So going back to the solar cells. So we've discussed a bit about the two potential types of solar cell materials. So we've got silicon and we've got perovskites. Could you tell us kind of a bit more about the specific material properties? Like what are they? Maybe we can start with perovskites.
Yeah, perovskites has a molecular structure of the type ABX3.
I don't know what that means.
It sounds like a K-pop.
Yeah. Exactly. No, so it's basically an inorganic metal halide compound. So it's got a lot of different compounds in there. Like I said, it's got a structure type called ABX3. So group A is an organic cation, so like methylammonium or formaldinium. Group B is normally a metal cation, which can be lead or tin. Lead is one of the more popular ones. And then group X is normally a halogen anion, so chloride, bromide, or iodide, or a mixture of these halogens. Yeah, so as you heard, they often use lead as the metal cation. And as you know, there's some toxicity associated with lead. So lead-free options are also being explored.
Very cool. And Laura, what about the silicon ones? How are they made?
So you start off with some really pure silicon, and then you dope it with either something that will lead to sort of, I guess, like a deficit in electrons when they bond to each other, or an excess of electrons, I think. So you generate something called a p-n junction. So you have these two slightly different compositions of silicon-based semiconductor, I should say. So the p-type might have boron in it, which makes it deficient in electrons, so as overall like positive charge. And the n-type commonly uses phosphorus in there, which generates a net negative charge. I think that's how I understand it anyway. Makes sense to me. P positive, N negative. It's a semiconductor, and I mentioned that band gap of 1.1 electron volts. So when the sunlight hits it, electrons are liberated and they can flow from that negative to positive type of semiconductor, and you get this charge that moves. I think the voltage is dominated by that band gap. So even if you shine more intense light on your solar cell, you won't generate more voltage. You might produce more current though, so you might have more electrons flowing, but you can't change that voltage. So that's what I read about how they work and how their composition affects how they work. So doping with the boron and the phosphor makes it easier to generate that current.
Very cool. So, but it seems like there's, in both cases, there's some pretty crazy materials involved in both of them. So we've got the lead for the perovskites, and then boron, and was the other lithium?
I mentioned phosphorus for the other.
Phosphorus. Sorry, meant to say
Yeah.
phosphorus. Yeah. Boron and phosphorus for the silicon one. So it seems it's quite complex.
Can I just ask, because it's quite interesting that you said you have N-type and P-type silicon solar cells. Do you combine the two layers?
Yeah, so you kind of sandwich them together, and there'll be this sort of, I think it's called like a deficit region in the middle where you've got something strange that don't really get my head around happens where the electrons flow.
Yeah.
And it's that difference, I guess, like the potential difference between the P-type and the N-type that helps generate that current. You generate it even if you didn't have the different types. It'd just be less efficient, I think.
It's a bit different in perovskites because it's like an ambipolar type of material. So when the perovskite absorbs a photon, it forms holes and electrons. And then the electrons are kind of separated. They transport through this electron transporting layer or titanium oxide, and then go to the anode, which is normally a type of conducting glass. And then the holes go through like a hole transporting layer, and then through to the cathode, which is often a metal made of gold or silver. So typically a perovskite device have 5 different layers with the perovskite sandwiched in the middle.
Okay. So when I was looking into it, I got the impression there might be more to it in the silicon-based ones, but I didn't know if they were doing what you mentioned, multi-junction cells before.
Yeah.
If it was some sort of multi-junction thing, or they were just overcomplicating it.
Yeah.
Because obviously you still need some layer that will stop the electrons from just going wherever the hell they want.
Right. Yeah.
But yeah, it does sound like the perovskites operate in a slightly different way.
Yeah.
My mind is just blown by how complicated both of the technologies. As someone who's not an expert, it's crazy that something as simple as harnessing the power of the sun, but the technology behind it is just mind blowing.
Well, you tried to make a Spider-Man reference there and go back to talking about fusion.
Maybe. Yeah, it's just self-serving. I have to bring it back to fusion every time, of course. But yeah, let's talk about climate change, because that's what solar cells are meant to be, one of the tools that we're using in order to combat climate change and move us away from using fossil fuels and other things. That means they should be sustainable, right? Solar cells should be sustainable if we're using them to combat climate change. But what do we really mean by sustainability? And are they actually sustainable?
We kind of talked about this in our What Do You Mean by Zero Waste episode a few months ago with Antonia and Cara, who are sort of experts in this sort of thing. We talked about it then in terms of you obviously want to gather your raw materials in a way that does the least amount of harm or even makes a place better than it was before. And then once you've used your product, you need to dispose of it responsibly or reuse it or recycle it in some way. You don't want to just send it to landfill. I don't really know much about where the raw materials come from, other than silicon is quite prominent in the world. But I do know that UK legislation means you can't just throw them away. You have to recycle them somehow. And any solar panel made within the last, I think it's 15 years, the producer has to take it back from you and use it responsibly. And I found wildly conflicting stories about how recyclable solar panels are or how reusable they are as well. They've got a design life of about 30-ish years. They gradually produce less electricity as they age, even though the conditions could be exactly the same. So you could stick your solar cell in a lab for 30 years and completely control the conditions, and it will still produce less electricity over time. just because materials change, they break down eventually.
So you can't recharge them, for example, and use them again after 30 years.
Yeah, there are things like cracks develop and things like that. Some of the problems that I read about didn't relate to the silicon material itself. It was things like electrical contacts break, or the glass that covers it that could shatter, or I think there's some sort of plastic covering as well that can turn brown because of sunlight. So lots of ways they can break that don't seem to have a lot to do with the silicon, which I was slightly surprised at in a way, because I always considered that because that silicon is a crystalline material and you're bombarding it with photons and you've got electrons flying around, that eventually bonds will break and defects will develop in that structure, which does affect their efficiency, but it's not the most common way that silicon solar cells fail, apparently. So you could refurbish them, I guess. You could replace the glass or fix the electrical contact.
And for the perovskites, is that the same thing, or is it more, as you said before, Jennifer, about the stability? So it's actually the perovskites themselves that degrade over time.
Yeah, I think it's more related to the perovskite itself. I'm also thinking about the fabrication. So the energy that needs to be put in to actually fabricate the solar cell, and then also the recycling bit, like how easy it is to recycle all the parts of the solar cell in the end. And for the recycling bit, I came across this interesting research paper that described how this can be done in further detail and how the cell can be disposed in a safe manner. And it seems like you're able to remove each layer, because like I said before, typically a perovskite solar cell would contain 5 different layers, and you are able to separate each of them and take them out for further processing. And then some of these layers can be reused later on, like the lead containing perovskite can be recycled and reused to make more perovskites or something else. And the most expensive part of the solar cell is actually the conductive glass that can also be reused for other purposes or for new perovskite solar cells. Another aspect of sustainability is obviously the lifetime of these solar cells. And I think as long as we have these stability issues, this is going to be a huge obstacle in actually, I don't know, reaching these sustainability goals or even commercial goals.
So you were saying perovskites don't last anywhere near as long as silicon-based solar cells. So I can imagine at the minute, most of the energy would go into producing the solar cell. So it takes more energy to produce the perovskite solar cell than the perovskite solar cell will produce over its useful life.
Yeah.
And you need to get that balance right.
Yes, although I wouldn't say they still last long, but probably not nearly as long as silicon-based solar cells. That's my take. But I think initially, when it comes to the amount of energy that's put into fabricate single crystalline silicon, that's much higher than, for example, fabricating perovskites, because it's just a solution-based process where you use spin coatings and you anneal the solution so that to settle the perovskite film. And the annealing process is done in quite low temperature, so below 100 degrees. But I think for silicon, it's much higher than that, right?
Yeah, because you want to get the silicon really pure to begin with, and then it sounds like you go through a whole range of steps, and it depends on exactly which manufacturer does what. Some of them use particle accelerators to dope the silicon, which I think sounds like wildly inefficient, because particle accelerators tend to consume a lot of electricity.
Yeah.
So we've kind of covered some key areas of sustainability there in terms of, the amount of energy it requires actually to manufacture these solar cells. I guess another key area of sustainable is, do they produce enough electricity for us to be able to use them? And I guess that depends where they're located. Maybe it's better if they're somewhere sunny, unlike Manchester, which is quite grey a lot of the time.
Funnily enough, I was just reading an article about how Dubai is a really inappropriate place for solar panels because it's too hot and they get less efficient at higher temperatures. And there's a lot of dust as well. So You cover your solar cell in dust and the photons can't come in, but the panel gets really hot and it becomes less efficient anyway. And apparently Dubai is just not the place to do it, even though it could be really sunny.
That's crazy. I'd never have thought that. I'd be like, that's the ideal place to put solar panels. So there needs to be like a kind of compromise in terms of climate conditions. So in that case, is it better to have the solar panels all in one place with the optimum conditions and then somehow transport the electricity we produce?
Yeah, this is what I wonder. See, if they work better at colder temperatures, are you better having them closer towards the poles of the Earth, where you obviously get sunlight for 6 months of the year at one pole and then the other 6 months of the year at the other pole, and it's really cold, right? So they should be really efficient, and then you just kind of oscillate between the two, so you've got a constant supply of electricity. I don't know, maybe that's a really stupid idea. Makes sense in my head though.
That's a very clever idea, I think. I like that. We just need a way to figure out how to transport the electricity we would produce, right? Which I guess is more of I feel there is technology to transport electricity. We do that every day, but it's very government specific. So I guess that requires political cooperation if we want to share electricity between many different countries.
Yeah.
Rather than a scientific
Yeah, I
one.
go for the science and everyone else. Well, the engineers say, no, you can't do that because of something else. That's what happened last week in our previous episode.
In some countries, the power grid system isn't as extensive. So it's more down to every individual to make that supply themselves with energy. So in this case, you would have more of a decentralized energy supply system where people would, maybe in this case, it would be better to,
to have your own solar.
Yeah, exactly.
Yeah, see, in a way, I prefer that idea because I have no idea exactly where my electricity comes from at the minute, and I don't really know what goes into making electricity get from where it is to where I am. But if there was a community of photovoltaics engineers and electrical engineers near me, and I could see the solar panels and I could talk to the people that ran them, I'd understand it better, and I think I'd feel a little bit more comfortable about using these things and not just taking them for granted.
Yeah, I agree with that. Like, you appreciate things more.
And I guess it's more accessible. I feel smaller things are always more accessible to people. Like if you have your own supply, then you control that basically. That's yours to do, and more people can use it. For example, people who grow heroin farmers in Afghanistan have made good use of solar technology. There was a really interesting article that we read. So that's one example of people taking control of their electricity production.
Not too sure the production of heroin is the best use there.
Not necessarily the best, but interesting nonetheless. But I also think one of the things that we've covered is that it's really complex technology. So that's another thing that makes me think, is it easy for people to maintain them if it breaks? Do you then need specific engineers to come in, or is it something you could fix yourself if there were any problems just because of the complex technology that's involved?
Yeah, so again, having some local engineers that know how these things work, I think would be more useful than just like sending it out to someone and saying, there you go, there's an electricity supply. You have to figure out how it works though.
Yeah. Is there any other simpler technology that we could use instead of solar panels to harness the sun?
There are like solar collection systems, aren't there? I mean, the way photovoltaics are going is they're getting more and more complicated. So they can try and make them more efficient. When Jennifer mentioned those multi-junction cells, that's effectively putting more and more layers of more complicated things that are made from different chemical elements that will use like different parts of the energy spectrum of the light that comes from the sun. Or we'll split the photon. So yeah, we seem to be going more complicated, but I didn't really come across much that was simpler.
In terms of solar cells. So there are these solar stoves that I've seen in Afghanistan, but it's like a giant mirror basically, lots of little mirrors, I think, and then they focus the light in the center. So people can use that for cooking and like for heating stuff pretty effectively without any emissions. So I found that a really nice, simple kind of technology. But yeah, I think if we want to produce electricity, the technology does seem to be kind of becoming more and more complicated.
Yeah, it would be nice if things went simpler because it means you're more likely to be able to maintain it, which again gives you that sense of I can use this thing and be a bit more self-sufficient rather than relying on the electrical engineers to come and fix my solar cell or replace the glass on it because it's cracked because of temperature differences or something.
Yeah, and I think that's for all technologies, right? A lot of stuff now we can't see how it works.
Yeah,
I find that really bad. Like, if you're phone breaks, you can't open it. If your laptop breaks, you have to take it. They will fix it. You can't fix it. Well, certain brands. Other brands are still better for laptops, but Apple especially is really bad for this. I feel another use of silicon. There we go. But not solar panels. But yeah, it's definitely something to think about.
Yeah, I was just looking up as we were talking. You're asking about where's better. Could you do it somewhere where it's really sunny? Apparently, the average installation in the UK can generate something like 3,000 kilowatt hours per year, but the average consumption is less than that per household, depending on the size of your house, of course. So in theory, it would be possible to generate all of your own electricity. And that's in like standard UK weather, so not being incredibly sunny and not being incredibly hot or incredibly cold, presumably.
That's great. So everyone should be getting solar panels on their houses.
Yeah, everyone in the UK anyway, but Dubai, you've still got a problem.
Which I really would have thought at the beginning of this episode, it would have been the other way around.
Did you know that the largest concentrated solar power plant project is in Morocco? It's called the Noor Power Plant.
That's very cool. And Noor means light.
Oh,
cool. I knew none of these things.
That's pretty cool that they're making a whole power plant out of solar cells, actually. I've never heard of that.
So is it currently sort of connected to their national electricity grid and supplying people's homes? Do you know?
No, I'm not sure. It looks like it's placed in the desert somewhere.
I wonder how dusty it is. Is it like Dubai and they have to clean it a lot?
I don't know. But it looks like it's going to cover an area of 2,500 hectares.
Whoa, that's massive.
Oh, yeah. No, it will supply electricity to their grid. That's pretty impressive.
Yeah.
That's awesome. It sounds like that's a good place to come to an end for the episode. I've definitely learned a lot. I think we've discussed the two main candidates for solar panels. The one that's currently used is the silicon solar panels, but perovskites are this really cool new technology that are accelerating at incredible speed. In less than 20 years they've almost got the same efficiency as silicon now, and it's more of a developing the longevity of the panels to make sure they're stable. We've discussed kind of what sustainability really means and considered the different parts of manufacturing process, how we get the electricity, where's the best place to put the solar panels. Apparently the UK is not bad. Who'd have thought it? So that's our take on solar cells. Find us on Twitter if you want to carry on this conversation, or leave a comment on the episode, and see you next time.
The views expressed in this podcast belong entirely to the person that said them. They do not represent any industry or organisation. If you enjoyed listening to these views, it would really help us out if you could rate us, leave a review and tell a friend. This podcast was sponsored by no one, but if you're interested in funding us to continue to have frank discussions about science and engineering, please get in touch.